Hello, in this video we are continuing our discussion of evaluating trigonometric integrals. We are talking about strategy 2, which is to use the Pythagorean identities along with a substitution. And in this example, we are asked to find the integral of tangent cubed x secant cubed x dx. Now, if you recall from the last couple of examples, we needed to first figure out what we had that was extra. The extra function, so that would become our du. Now, in order to do that in this case, we need to figure out what sort of derivatives we may have in this problem. So our possible choices for u. So we have two functions here, tangent and secant. So that would be a place to start. We could try u equaling tangent. We could try u equaling secant. Well, u equaling tangent would mean that du is secant squared x dx, or if u was secant x, then du would be secant x tangent x dx. We also want to keep in mind that the identity we're going to use here, the Pythagorean identity, involving secant and tangent is, tangent squared x plus 1 equals secant squared x. So we have squared powers of both tangent and secant. So keep that in mind when we're trying to figure out what we have that's extra. If we were going to use u equaling tangent x, then du would be secant squared x, so we would need a secant squared split off here, so that would give us secant x times secant squared x, but then we have two odd powers of both tangent and secant, so we can't substitute in here using the Pythagorean identity. So what that means is u equaling tangent x won't work. So instead, that means that we need to use our second option. So using u equaling secant x and du equaling secant x tangent x dx. Then we need to have a secant x tangent x reserved in our integral. So we are going to rewrite the integral of tangent cubed x secant cubed x dx as the integral of, we need a secant x tangent x dx at the end. So that means we're going to take one of our tangent x's. So we'll rewrite this as tangent squared x times tangent x. And the secant we'll rewrite as secant squared x secant x, so that we end up with the integral of tangent squared x secant squared x, and then secant x tangent x, and now we have our du reserved here. Well, u in this case is secant x, so this means that we need tangent squared x in terms of secant x, and we're going to do that by rearranging our Pythagorean identity so that the tangent squared of x is equal to secant squared x minus 1. Okay, so then our integral of tangent squared x secant squared x times secant x tangent x dx will equal the integral of secant squared x minus 1 times secant squared x times secant x tangent x dx. Now we can substitute in for u and du, so we get the integral of u squared minus 1 times u squared times du. If we distribute our u squared, we will get the integral of u to the fourth minus u squared du, and now, like with the last couple of examples, we just have a couple of simple antiderivatives. So we have 1/5 u to the fifth minus 1/3 u cubed. We do need to remember to add a c since this is an indefinite integral, and our last step is to substitute back in for u, so that is going to be 1/5 secant to the 5th x minus 1/3 secant cubed x plus c. So our final answer then is the integral of tangent cubed x secant cubed x dx is equal to 1/5 secant to the 5th x minus 1/3 secant cubed x plus c.